Yes, sir.
Screen visible.
Okay. So we are continuing from that modeling of I naught and the formula and the equation for I naught being this part. I was talking about why AVT. Why AVT, this term, it we are not reciprocal of 1 by AVT or directly multiplying AVT for this part. I am directly multiplying with this. For later on, while we will model for AVT, that VT term is given VT equal to NS KT by Q, and AVT will be A NS KT by Q, and reciprocal of this will take actually Q by A NS KT. So while modeling, that part will be reciprocal of that AVT will take, and directly multiplying that AVT over here for that purpose only. So up to this part is over. So to get the exponential, we will take one math function. We make it cube math function. So right now it is exponential of VOC plus KV delta T by FVT, and one should be subtracted from the term to get the total overall denominator part. So a constant term, constant block will take the constant block, assigning the value as 1, and finally we are getting the denominator part. And for regarding numerator, it is ISCN KI delta T. ISCN KI delta T. So one ISCN. What is the value of ISCN? 0.3. ISCN 8. That value is 8.21. So we can assign the value 8.21 ISCN plus ISCN plus KI, another constant term, that value 0.0032 ISCN plus 0.0032 into delta T. Delta T we can directly take this one. And multiplied now this numerator part and denominator part is over. We'll take one divide block, directly taking from here, and this is nothing. This is the I naught. Now from this slide, we have already modeled IPV and I naught. Then coming to modeling of IM. For modeling IM, the formula says IM equal to IPV minus IPV or IPS minus ID divided current. That is ID equal to I naught exponential V plus IRS by AVT minus T. So referring to that formula only, I am taking This is V. First I'm completing that V plus IRS. V plus V plus I, and RS value is also given. What is the value of RS? 0.221. RS series resistance value is given 0.221. So another constant I will give value 0.221. So I into RS is what is over. V plus I into RS divided by AVT. I have already told that directly you can take that term from here, AVT, that can be multiplied. Actually, it is the reciprocal already we have taken, reciprocal of AVT. This is 1 by AVT. That's why this term clarifies V plus IRS divided by AVT, and one exponential term we need to take. That's why this math function right now it's exponential of V plus IRS divided by AVT minus 1. Minus directly minus 1, we can also assign the constant term minus 1. So I think this part is over. Exponential of V plus IRS AVT minus 1, and it should be multiplied with I naught. So I naught is already calculated. So it should be multiplied with I naught. That's why now it's multiplied with I naught. IPV minus. So this is IPV IPV minus I naught into that exponential term, which is IM. So this is the now it completes the modeling of IM, that is IPH or IPV minus ID. So everywhere I have taken here IPH. It is better to take the same variable name IPH. So now we don't have any idea regarding that what is that voltage, this voltage and this current, output voltage and output current of the PV model we are considering. That's why we will go for modeling the equivalent circuit of that PV cell. So first of all, before that AVT part is also left. The formula for AVT says it is reciprocal. Actually, it is 1 by AVT, which is Q divided by NS KT. Q divided by NS KT. So, one constant taking 1, 2, 3. First one I am assigning as A, that is the modulo identity factor. For the same, it has been assigned 1.3, and that is K value. K value is also given, that is Boltzmann's constant, 1.38605, 1.38605, 1.38605 e to the power 5 e to the power minus 23. Then another constant is NS. NS is taken as 54. NS is 54. So now PT should be multiplied these three constant values are multiplied, then Q, another constant is Q, that is charge of one electron. This value is also given, 1.6 10 to the power minus 19. 1.6 e to the power minus 19. So this is divided, Q divided by this term, then another whole divided by T, that is also whole divided by T. It's the final value of AVT. So this part is over. Right now the circuit total, the PV circuit will do, where the controlled current source, that IM acts as a controlled current source. Controlled current source will take controlled current source and a shunt resistance is required, which is RSH, and a series resistance RS. The values are also given. So I'm searching for one series RLC branch, and we need only the resistance part. That's why resistance, and for series it is 0. Already we have taken 0.221. Another resistance value we need 415, the value being 415.405. So now this has to be connected in series and this has to be connected in parallel. Like, we need to so now I need to draw the complete model, the complete circuit for finding the values of voltage and current, which are those right now only two variables are there, the cell voltage and output current. So then the voltage measurement block and a current measurement block for measuring the same voltage measurement block, control F means so directly I can connect to here and it is connected over here. And for voltage measurement part also, a controlled voltage source that has been taken and one, and this will give the total output voltage of the cell, that is capital G output voltage. Similarly, another go to block we can take to record the total output current. So and from block. So now it completes the circuit of the series cell we are considering. But here another thing block we need, that is a saturation block for setting the limit saturation. Also a ramp signal. So yes, we are getting the output voltage, setting the upper limit is 32 points. Upper limit 32.899. I'm setting 32.9, the maximum limit I'm giving, and the lower limit being 0 or 0.001. And by default, the ramp signal is slow being 1 and the start time 0 and initial output being 0. And for seeing the output current as well as voltage, display block we can use. This is for I and this one for output voltage V. Finally, for plotting purpose, we can do this one I, this one V, I and V. We are making one product to get the power or calculation. So directly to XY graph block we can take to plot directly the same. So in IV curve, our V is taken in x-axis and I is taken in y-axis. For that purpose, here we should mention that x-axis should be voltage and y-axis being the current. Another XY graph we can take. Here x-axis being the voltage and y-axis being the power in PV curve. Sorry, disconnection. Power. Also, for plotting several conditions, means like at different irradiance values, like 1000 watt per meter square, 800 watt per meter square, 600 watt per meter square, and keeping the constant temperature, that is 25 degree, or or 20, or that value being constant. So we need to take it to workspace. So to workspace, clock will use to workspace and rename it as three number of workspace eligible. First one IPV I am taking IPV. And the decimation being 1, right? And time series array. Another thing is V, PV, and the last one being P, PV. Here also is a format being array. So this one is my IPV. I'm denoting this one as IPV, taking to workspace, and this is the VPV, and the last one is PPV. Also for directly recording the values, also we can connect three displays for IPV, VPV, and PPV. Now on for V block, in the simulation time, so let me summarize the same thing. First of all, I declared the values for temperature and the irradiance, then went for the modeling of IPH, then modeling of I naught, then modeling of IM. Then how to get the value for output V, two variables voltage and current. Finally, we are plotting the VI as well as PV curve. IPHN. This is the translation. This one is happening. Okay. I'm saving the same. So model to this curve is now this one is the PV curve going to this telling it to 0, 0. So we have the PV curve and this is the IV curve for the same model. And the ISN being 8.29. And for the particular experiment, so we can draw the PV as well as the IV curve for different irradiance values, making the command, golden command. So as the objective shows simulation of a solar panel at various level of insolation or temperature, plotting IV and PV curves. Particularly for the same model, we can go for different irradiance values, keeping the temperature constant and keeping the irradiance constant and the temperature value being varied, that is 25 degree, 30 degree, 35 degree, like this. So now coming to the second objective, so to draw the various characteristics of a PV panel by varying the load resistance. So for this, so I have directly taken the PV array from the library. You can notice that is Kyocera Solar KC200 GT, and the maximum power of the panel all cells for module and open circuit voltage, all the parameters are already given. But the thing is that in this case we need to calculate the value of the parameter we need to estimate using the VI curve only. And how to we make calculate those values, I will just have a brief explanation about this, then only I can proceed for the simulation part. In parameter estimation, as we know, the intensity of the irradiance is directly proportional to the that IPS value. That means according to the photocurrent, IPS is determined the irradiance value, the intensity of the irradiance. And the parameters, 5 parameters we need to calculate in this case, that is IPS, I naught, that is the saturation current, photon current, and the diode identity factor A, and series resistance as well as the shunt resistance. How we can calculate those values, those parameters from the PV curve itself? We can notice from the VI curve of the solar panel that at ISC, means at I equal to ISC, so we can have a slope of the curve, that is dI by dV, when V equal to 0 or short circuit condition, and it is denoted by 1 by minus negative of reciprocal of RSS naught, where RSS naught is the reciprocal of gradient at the short circuit point. Similarly, another parameter from that VI curve itself we can find, that is at open circuit condition, the DI by dV at I equal to 0 or at open circuit condition, that is termed as reciprocal of the gradient and the open circuit point. So RSS not equal to, from here RSS not equal to negative of dV by di at V equal to VOC, and RSS not equal to minus negative of dV by di at I equal to ISC naught. So from the curve we can have two different points, like that the voltage VOC approaching, let VOC equal to already 32.9. We can choose two different points, 32.9 or 32.85, two different points. For two different points, we can get the slope value. That slope value will yield negative of 1 by RSS naught. Similar way, we can find those parameters. In this case, our RSS will be equal to RSS naught, but the RS series resistance value will will be a little less than that of the exactly value we are getting from the slope value. And it is given in the equation number 6, that is RSS E equal to RSS RS E equal to RS naught minus this term AVT by I naught exponential of negative of VOC by AVT. So this part already it will take time for modeling the same. Already according to that first modeling case, this part has also been modeled, and taking the reference of all these equations. The thing is how we are calculating the parameters whenever we are directly taking one PV array from the library itself, that we need to see. So here standard condition I have given, irradiance being 1000 and temperature 25 degree, and for different values of resistance values, I will get different values for voltage, IPV as well as VPV, and from IPV and VPV I will record the values for different power PPV, and I will make one tabulation for recording I, P and V, so that I can easily get the curve for I and VI curve as well as PV curve for the given panel. So let I am going for one value. I am checking just 0.25 ohm. I am taking the values for resistance, load resistance, and what should be the I value as well as V value. I need to see. So for the load resistance being 0.25, I am getting IPV 8.196 and VPV being 2.049 volt. So this has been already recorded in this tabular format in observation table. For 0.25, this is VPV being 2.049 and 8.196, and power also being calculated. Like this, we'll go on increasing the load resistance starting from 0.1 to 0.25 up to some higher value, so that we can get the IPV value, the minimum IPV value, or we can toss the open circuit condition. So that after getting this tabulation directly in Excel or on MATLAB platform also, we can draw the curve for IPV versus VPV and PPV versus VPV, PV curve and IV curve we can plot. Now the point is how to estimate the parameters from plotting the IPV, IV and PV curve. Already as I have explained here, from here we can make use of two different adjacent points. That means in this case at 8 point something, that is the short circuit position, we can take 8.2 similar, like this here we have taken 8.21 or 8.208, 8.21, 8.208. According to that, if we'll put those values, we can record one voltage value. Like in this simulation here, I am using one controlled voltage source, so that I can change the value of the voltage, open circuit voltage, two different values to record to adjacent corresponding value of the current. So according to the table 4, I am making VPV as 0 and 1, and I'll notice what is the change in IPV value. Let's I am putting it 0. That means it is a short circuit condition. When I am putting the voltage at 0, what is the value of current I am recording? It is 8.21001. So that is updated in this table 4. VPV1, VPV equal to 0, IPV equal to 8.21. In the similar way, another value I have taken 1. That is, I am changing this constant voltage value, that is 1, and noticing what is the change in current, that is 8.20339. Also the power value is changed, but we don't have anything to do with that power right now. For the getting the parameter like RSS and RS naught, we need to get the value of these two points we need to get. That purpose only we are changing that constant voltage value to that 0 and 1, and already this value for corresponding to 0 we are getting 8.21, corresponding to 1 we are getting 8.20, and this is particularly the short circuit condition. And for short circuit condition, is which parameter we need to get? At short circuit condition we need to get RSS naught. So RSS naught can be calculated referring to this table number 4. In the similar way, I am changing that. I am going for the open circuit condition, where that controlled voltage source can be fed with a voltage approaching to maximum open circuit voltage, that is 32.9. If I am giving 32.9, and I'm recording the current to be minimum at that time, being -0.00233, and another value, let it be 32.8. So 32.8, it is 0.1914, and that has been updated here. 32.89 minus 0.03743, 32.8, 0.1867. It is particularly operating we are operating at the open circuit condition and finding the parameter of from this curve. In open circuit condition, we are finding the parameter for RS naught. From RS naught, so from RS naught, we can calculate RSE referring to the formula equation 6. Another identity factor, for calculating identity factor, we have everything, all these known parameters from the panel we have taken, like VMPP, RSS naught is already calculated, IMPP is given, V open circuit and VT, all these parameters are known, can easily be calculated from that. Only main parameter to parameter, that is the series resistance and shunt resistance, from the VI, plotting the VI curve we can get, and these parameters can be make use in calculating the identity factor, calculation of identity factor. So in the observation table, I have already told how we plotted that VI curve as well as PV curve. Then we move forward to take the experimental data, that is varying the value of that voltage VPV approaching to 0 and 1 to get two different points coordinates, and the same thing we are approaching to maximum value of that is 32.9 and 32.8 to get two coordinates to calculate the slope only, and that slope is the parameter like RSS and RSE. And finally, as you noticed from the PV array we have taken, that is Kyocera 200 GT here, Kyocera Solar KC 200 GT, its identity, all these things is for that only. Finally, we need to identity factor N, actual and estimated value after calculating, and series resistance and shunt resistance value we have already mentioned. Whatever we have mentioned in the parameter section, we need to verified over here after calculating, and yeah, it approaches and it goes for as per the modeling. And this part, another thing, for calculating these values, we can directly make use of one MATLAB programming for parameter calculation. All these formula, taking all these formula like RSS not, RS VMPP is given, all these things. So this MATLAB program can yield the values for like here. RS equal to 0.2212 and RS is not equal to 0.44. RS not equal to 0.4458. RS equal to 0.2212 like this. So this concludes the total experimental means lab session for calculate how to estimate the parameter of a solar panel directly, whichever we can take from the simulating environment, and plotting the VI curve or PV curve, how we can estimate the parameter like the shunt resistance as well as the series resistance and the diode ideality factor of the same panel we are considering. You can take your time to do the same at your home, but in this MATLAB platform, whatever I have already told, this is the simple way to first model the PV panel, and getting through the whenever a panel is already given, taken, how to estimate the parameter. Following to the simple equations, we can also complete the same thing. So this concludes the session. Any queries from any participants can ask. Is it audible? Am I audible to all of you?
Yes, you are audible.
Participants, if anyone has any doubts, please ask. So I hope there is no doubts from audience side. So I would like to say thank you to Mr. Bibhudatta Mishra for such a informative session on parameter estimation of solar panels. Thank you. Thank you so much.
Thank you, Amanda.
And we'll resume our session at 4:15 p.m., which will be taken by Professor Arnab Ghosh from NIT Rourkela. Thank you.